Hello guys, welcome back to my channel, and on today's video I'll be explaining Prim's algorithm. It is one of the most important algorithms used in graph theory and network optimization. Prim's algorithm is designed to find a minimum spanning tree, often abbreviated as MST, from a connected weighted graph. In this video, I will explain what Prim's algorithm is, why it is useful, and the key concepts required to understand it. The step-by-step process it follows and how it selects edge based on minimum weights. Finally, I will demonstrate the algorithm using a practical example and show how the minimum spanning tree is formed. By the end of this video, you should have a clear understanding of how Prim's algorithm works and where it can be applied in real-world situations. So, without further ado, let's get started. So, what is Prim's algorithm? Prim's algorithm is a greedy algorithm used to find a minimum spanning tree in a connected weighted graph. It was developed by Robert C. Prim in 1957 and has become one of the standard algorithms taught in computer science and mathematics. A graph is made up of vertices, which are also called nodes, and edges, which connects the nodes. In a weighted graph, each edge has an associated numerical value known as a weight. This weight can represent distance, cost, time, or any other measurable quantity. The purpose of Prim's algorithm is to connect all vertices while ensuring that the total weight of the selected edges is as small as possible. Unlike some other algorithms, Prim's algorithm grows a single tree from a starting vertex until every vertex in the graph becomes a part of the tree. So, what is the purpose of the Prim's algorithm? The primary purpose of Prim's algorithm is cost optimization. In many real-world situations, we need to connect multiple locations while minimizing the total cost involved. For example, imagine a telecommunications company that wants to install internet cables between several cities. Connecting every city directly to every other city would be extremely expensive. Instead, the company can use Prim's algorithm to determine the set of connections that links all cities together with the lowest possible installation cost. Other applications include designing road systems, electrical power grids, water supply networks, railway systems, and computer networks. In each of these cases, the objective is the same: connect all locations while minimizing the overall cost. Before we examine the algorithm itself, let's review some important concepts. The first concept is the graph. A graph consists of vertices and edges. Vertices represent objects or locations, while edges represent connections between them. The second concept is a weighted graph. In a weighted graph, every edge has a value called a weight. This value may represent a distance, cost, or another measurable factor. The third concept is a spanning tree. A spanning tree is a subset of edges that connects all vertices in a graph without forming any cycles. Finally, a minimum spanning tree is a spanning tree with the smallest possible total weight. There may be several spanning trees in a graph, but the MST is the one with the minimum total cost. Prim's algorithm helps us find this optimal solution efficiently. Now let's look at the steps involved in Prim's algorithm. The algorithm begins by selecting any vertex as the starting point. This vertex becomes the first member of the minimum spanning tree. Next, we examine all the edges connected to the current tree. We identify the edge with the smallest weight that connects the tree to a vertex that has not yet been included. We then add that edge and the new vertex to the tree. This process continues repeatedly. At every stage, we select the minimum weight edge that expands the tree while avoiding cycles. The algorithm stops when all vertices have been included. At that point, we have constructed the minimum spanning tree. Now I'm going to explain the selection of edges based on minimum weight. The edge selection process is the key feature of Prim's algorithm. At each step, the algorithm only considers edges that connect the current tree to vertex outside the tree. Any edge that would create a cycle is ignored because spanning trees cannot contain cycles. Among all eligible edges, the algorithm selects the one with the smallest weight. This is why Prim's algorithm is called the greedy algorithm. It makes the best local choice at each step without reconsidering previous decisions. Although the algorithm focuses only on the current step, it can still guarantee an optimal minimum spanning tree. This makes it both simple and highly efficient for many applications. For better understanding of the Prim's algorithm, let's examine a sample graph. The graph contains five vertices labeled as A, B, C, D, and E. The edges connecting these vertices have different weights. For example, the edge between A and B has a weight of 2, while the edge between B and C has a weight of 1. Our goal is to use Prim's algorithm to find the minimum spanning tree. We will begin at a vertex A and follow the algorithm step by step. As we proceed, pay attention to how the algorithm always chooses the smallest available edge that expands the tree. Now let's see how the iteration process works. First, we start at vertex A. Initially, the tree contains only A. The available edges are AB with weight 2 and AC with weight 3. Since 2 is smaller than 3, we choose the edge A and B. The tree now contains vertex A and B. Next, we look at all the edges connecting to the current tree to unexplored vertex. These edges are B and C with the weight of 1, B and D with the weight of 4, and A and C with the weight of 3. Among these options, B and C has the smallest weight. Therefore, we select edge B and C and add vertex C to the tree. At this stage, the tree contains vertex A, B, and C. And now we continue building the tree. The remaining vertices to be connected are D and E. The available edges are B to D with a weight of 4, C to D with a weight of 5, and C to E with a weight of 6. The smallest edge is B to D with a weight of 4. So we select it and add vertex D. Now only vertex E remains outside the tree. The possible connection to E are D, D to E with the weight of 2 and C to E with the weight of 6. Since 2 is smaller than 6, we select D to E and add vertex E. At this point, every vertex has been connected. The algorithm stops because the minimum spanning tree is complete. Notice that at every step we selected the lowest cost edge that expanded the tree. This is exactly how Prim's algorithm operates. And now let's summarize the results. The edges selected for the minimum spanning tree are A to B with a weight of 2, B to C with a weight of 1, B to D with a weight of 4, and D to E with a weight of 2. Adding these weights together gives a total weight of 9. This means that all 5 vertices have been connected with the minimum possible total cost. Also, if you look, there's a diagram of the output, or the final MST. So, in conclusion, Prim's algorithm is a powerful and efficient method for finding a minimum spanning tree in a weighted graph. It uses a greedy approach, selecting the smallest available edge at each step while avoiding cycles. Because of its efficiency and practical applications, it is widely used in network design, transportation systems, electrical distribution networks, and many other optimization problems. That's the end of our video. Thank you for your attention, and I hope this video has helped you understand the purpose, process, and application of Prim's algorithm. and I'll see you guys in the next video.